Tonight, we are going to explore something you interact with every second of your life, yet may never have truly understood. The electron. You have heard the word before. You know it has something to do with atoms, electricity, and the structure of matter. But what an electron actually is turns out to be far stranger than the simple pictures most of us grew up with. It is not a tiny ball. It is not a miniature pebble hidden inside the atom. And once you understand what it really is, you may never look at the physical world in quite the same way again. Because here's the astonishing truth. You have never actually touched anything. Not once. Not in the ordinary sense we imagine. Not your chair. Not your phone. Not the floor beneath your feet. Not even the hand of another person. What you experience as touch is something else entirely. Something deeper, more elegant, and far more mysterious. That idea sounds impossible at first. After all, the world feels solid. Surfaces feel firm. Objects seem to press against one another. But when we look beneath ordinary experience, down to the level of atoms and electrons, the familiar picture begins to dissolve. The story begins with matter itself. Everything around you. The air. The walls. Your body. The device playing this audio is made of matter. For most of human history, no one knew what matter truly was. People could shape it, break it, melt it, burn it, and build with it. But its deepest structure remained hidden. And yet, more than 2,000 years ago, a few thinkers guessed that beneath all visible things, there must be smaller invisible units. They did not have microscopes. They did not have particle accelerators. They only had thought, patience, and curiosity. And strangely enough, they were pointing in the right direction. Tonight, we follow that trail, from ancient ideas to modern physics, from atoms to quantum fields, and from the simple question of what an electron is, to the breathtaking realization that the solid world around you is not quite what it seems. Long before modern science, ancient Greek philosophers tried to explain what matter was made of. Some believed everything came from four basic elements: earth, water, air, and fire. It was a neat and beautiful idea. If all substances were just mixtures of these four ingredients, the world became simple and understandable. But nature, as it turns out, is rarely that simple. Another idea came from Democritus, who lived around the 5th century BCE. He imagined taking a piece of matter and cutting it in half, then cutting those halves again and again, until eventually you reached a piece so small it could no longer be divided. He called this smallest unit atomos, meaning uncuttable. It was a remarkable intuition, especially for a time with no experimental tools to test it. For more than 2,000 years, that idea remained largely philosophical. Then chemistry began to mature. By the 19th century, scientists had strong evidence that matter really was built from atoms, and that each chemical element had its own kind. Hydrogen was one kind of atom. Oxygen was another. Carbon, iron, gold, nitrogen, each had distinct properties and behavior. Then came Dmitri Mendeleev, who arranged the known elements into what became the periodic table. The patterns were striking. The table hinted that atoms were not random little pieces, but part of a deeper order. Still, most scientists imagined atoms as tiny solid spheres, indivisible and fundamental. That picture did not survive the end of the 19th century. In 1897, J.J. Thomson studied mysterious beams called cathode rays inside glass tubes. By observing how these beams bent in electric and magnetic fields, he discovered that they were made of negatively charged particles, far smaller than atoms themselves. This was revolutionary. If something smaller than an atom existed, then the atom was not indivisible after all. Thomson had found the electron. Suddenly, the atom was no longer the final layer of reality. It had structure. It had parts, The supposedly uncuttable had been cut open. And once that door was opened, physics would never close it again. For a brief moment in history, scientists believed they had reached the end of the story. The atom, they thought, was the smallest possible unit of matter, a solid, indivisible sphere. Simple, complete. But that idea did not survive the next experiment. After discovering the electron, J.J. Thomson proposed a model of the atom that tried to make sense of this new particle. He imagined the atom as a kind of positively charged sphere, with negatively charged electrons embedded throughout it, like raisins in a pudding. It became known as the plum pudding model. At the time, it seemed reasonable. It explained why atoms were electrically neutral. It explained how electrons could exist inside them. But like many early models in science, it was only a stepping stone. In 1911, another experiment changed everything. At the University of Manchester, Ernest Rutherford and his colleagues fired tiny, positively charged particles at an extremely thin sheet of gold foil. According to the existing model, these particles should pass straight through, perhaps with slight deflections, and most of them did, but not all. Some particles were deflected at sharp angles. A few even bounced almost directly back toward the source. Rutherford was stunned. He later compared it to firing a cannonball at tissue paper and having it come straight back at you. There was only one explanation. The positive charge inside the atom was not spread out. It was concentrated in an incredibly small, dense region at the center, the nucleus. This discovery transformed our understanding completely. The atom was no longer a solid sphere. It was mostly empty space, with a tiny, dense nucleus at its core, and electrons occupying the vast region around it. To grasp how empty an atom really is, imagine this. If the nucleus were the size of a small marble placed at the center of a football stadium, the electron would not be circling neatly nearby. It would exist as a diffuse presence, spread out across the entire stadium, even beyond it. Not a point, not a particle in a fixed path, but something far less intuitive. And this raised a serious problem. According to classical physics, an electron moving around a nucleus should continuously lose energy, radiating it away as electromagnetic waves. It should spiral inward and collapse into the nucleus almost instantly. But that does not happen. Atoms are stable. Matter exists. You exist. So something in our understanding was fundamentally incomplete. To solve this problem, physics had to change in a very deep way. In 1913, Niels Bohr proposed a bold idea. He suggested that electrons do not move in just any orbit around the nucleus, but only in specific allowed energy levels. Not continuous motion, but discrete steps. An electron could exist in one level or another, but never in between. It could jump from one level to another by absorbing or emitting a precise amount of energy, a quantum. This idea worked surprisingly well, especially for hydrogen. It explained why atoms emit light at specific frequencies, forming distinct spectral lines. But it was still only part of the truth. Because even in Bohr's model, electrons were treated as tiny particles, moving in defined paths. And nature, once again, turned out to be stranger than that. In the 1920s, a new idea emerged, one that would completely reshape physics. Louis de Broglie proposed that particles like electrons do not behave only as particles. They also behave as waves. Not metaphorically. Literally. Every electron has a wavelength. And for something as small as an electron, that wavelength is not negligible. It is comparable to the size of the atom itself. This idea was confirmed through one of the most famous experiments in science, the double-slit experiment. When electrons are fired one at a time through two narrow openings, something remarkable happens. Each electron lands on a screen as a single point, like a particle. But over time, the pattern that builds up is not what particles should produce. It is an interference pattern. the kind of pattern you only get from waves. This means that each electron behaves like a wave, passing through both openings at once, interfering with itself. But when it is detected, it appears as a single localized event. This dual nature, wave and particle, is not a flaw in the experiment. It is a fundamental property of reality. Electrons are not tiny balls moving along paths. They are described by probabilities. In 1926, Erwin Schrödinger introduced the equation that captures this behavior. Instead of telling us where an electron is, it gives us a wave function, a mathematical description of where the electron is likely to be found. Not certainty, probability. The electron does not sit at a fixed point waiting to be discovered. It exists as a spread-out distribution of possibilities, a cloud. And only when we measure it does it appear at a specific location. This was the moment physics stepped fully into the quantum world, a world where particles are not really particles, where certainty is replaced by probability, and where the familiar solid picture of reality begins to dissolve into something far more subtle. Up to this point, the electron may still feel like a strange kind of particle. Something small, something real, something that exists somewhere, even if its position is uncertain. But modern physics asks us to go one step further. Because even calling the electron a particle is, in a deep sense, misleading. To understand what an electron truly is, we need to move beyond quantum mechanics into a deeper framework known as quantum field theory. In this picture, the fundamental ingredients of reality are not particles at all. They are fields. A field is something that exists everywhere, in space, not just in one location, but at every point. You already know examples of fields, even if you don't think of them that way. Temperature is a field. At every point in a room, there is a temperature value. Gravity is a field. At every point in space, there is a gravitational influence. Quantum field theory says the entire universe is filled with fundamental fields. There is an electron field, a photon field, quark fields. These fields are not inside space. They are space, in a very real sense. And here's the key idea. An electron is not a tiny object sitting inside the electron field. An electron is a localized excitation of the field itself, a disturbance, a ripple. A useful way to imagine this is to think of the surface of a calm ocean. The ocean is always there, spread out across the entire basin. When energy passes through it, waves appear. But the waves are not separate objects floating on top of the ocean. They are the ocean, temporarily taking on a different form. In the same way, the electron field is always present, everywhere. And what we call an electron is what happens when that field vibrates in a specific quantized way. This is why electrons are identical everywhere in the universe. Not similar, identical. Every electron has exactly the same mass, the same charge, the same intrinsic properties, because they are all excitations of the same underlying field. So when you hear the word electron, do not imagine a tiny ball. Imagine a ripple in something that fills all of space, something with no known size, no internal structure, but with very precise, measurable properties. A ripple that behaves like a wave when it spreads out, and like a particle when it is measured. And already you can begin to see the implication. If the building blocks of matter are not solid objects, but excitations of fields, then the idea of solid contact becomes much less obvious. Now that we understand what an electron is, we need to understand how electrons behave when there are many of them. Because everything you see, everything you touch, everything you are made of, depends on how electrons arrange themselves. And here, we encounter one of the most important rules in all of physics, the Pauli exclusion principle. This principle is simple to state, but its consequences are enormous. No two identical electrons can occupy the same quantum state at the same time. That means if two electrons are in the same region of space, they cannot have exactly the same set of properties. If one electron is already in a specific state, another electron is forced into a different one. This rule is not a suggestion. It is absolute, and it is the reason the universe has structure at all. Without it, all electrons would collapse into the lowest possible energy state. Every atom would look essentially the same. There would be no chemistry, no diversity of materials, no complex structures. But because of this rule, electrons are forced to spread out. They fill different energy levels around the nucleus, forming what we call orbitals. Not paths, but regions of probability, where electrons are most likely to be found. Each orbital can only hold a limited number of electrons. Once it is full, additional electrons must occupy higher energy levels, farther from the nucleus. This creates layers, structure, complexity. It is the reason hydrogen behaves differently from helium, the reason carbon can form complex molecules, the reason oxygen supports combustion, the reason your body can exist as a stable, organized system, and it leads to something even more profound. When two atoms come close together, their electron clouds begin to overlap. At that moment, the Pauli exclusion principle begins to resist. Because now, electrons from different atoms are being pushed into the same regions of space. And the rules of quantum mechanics do not allow them to simply merge into identical states. So what happens instead is this: the system pushes back. Electrons are forced into higher energy configurations, and that increase in energy creates a powerful resistance, a kind of invisible pressure. Combine this with the fact that electrons all carry negative charge, and therefore repel each other electromagnetically, and something remarkable emerges: an effective barrier. Not a wall, not a surface, but a force, a resistance that grows stronger the closer atoms come together. And this is the beginning of what you experience as solidity. Now let us return to something simple. You place your hand on a table. It feels solid, stable, real. Your palm presses down and the table pushes back. Every signal in your body tells you the same thing. You are touching it. But at the atomic level, something very different is happening. Your hand is made of atoms. The table is made of atoms. And as we now understand, atoms are not solid objects. They are mostly empty space, with a tiny nucleus surrounded by a cloud of electron probability. These electron clouds do not have hard edges. They fade gradually into space. There is no sharp boundary where an atom suddenly stops. The same is true for the atoms in the table. So as your hand moves closer, the first thing that happens is not contact, but overlap. The outer regions of the electron clouds in your skin begin to extend into the outer regions of the electron clouds in the table. And the moment this overlap begins, two powerful effects take over. The first is electromagnetic repulsion. Every electron carries a negative charge, and like charges repel. As the electrons in your hand get closer to the electrons in the table, the repulsive force between them increases rapidly. The closer they get, the stronger the push. The second effect is the Pauli exclusion principle. Electrons are identical particles, and when their probability clouds begin to overlap, they are effectively being forced into similar quantum states in the same region of space. But the rules do not allow that. So instead, the system resists. Electrons are pushed into higher energy configurations, and that increase in energy manifests as a force pushing back against your hand. These two effects, electromagnetic repulsion and quantum exclusion, combine to create a barrier, not a surface, a force. And this force becomes incredibly strong at extremely small distances on the scale of about 1 angstrom, roughly 1/10 billionth of a meter. Your hand never gets closer than this. Not because it can't move further, but because the forces resisting it grow so strong that they balance your push perfectly. So what you feel as touch is not contact between objects. It is the sensation of forces. Your nervous system detects the pressure created by these interactions and translates it into the experience of solidity. It feels like contact, but physically, it is something else entirely. This idea does not just apply to your hand and a table. It applies to everything. When you sit in a chair, you are not resting on a surface in the classical sense. The atoms in your body are being supported by electromagnetic forces from the atoms in the chair. You are, in a very real way, hovering. The gap is unimaginably small, far beyond anything your senses can detect, but it is there. When you walk across the floor, your feet never make contact with it. Each step is supported by the same invisible balance of forces between electron clouds. When you pick up an object, your fingers do not grip it by touching it. The resistance you feel comes from electromagnetic interactions between the atoms in your skin and the atoms in the object. Even friction, the force that allows you to hold things, walk, and move, is not caused by surfaces scraping against each other in the way we imagine. At the microscopic level, friction arises from countless tiny electromagnetic interactions between irregular surfaces. As materials slide past each other, electron clouds form and break temporary interactions, releasing energy as heat. Nothing is grinding. Everything is interacting. Even something as simple as warmth is part of this picture. When you touch something warm, energy flows into your skin through electromagnetic interactions between atoms. When you touch something cold, energy flows out. Your nerves detect these energy transfers, and your brain interprets them as temperature. Smoothness, roughness, hardness, softness, all of it emerges from how electron clouds are arranged and how they interact with your body. A smooth surface produces consistent, uniform interactions. A rough surface produces rapidly changing ones. Your brain translates these patterns into sensation. And because these interactions are so consistent, so reliable, and so strong at human scales, your mind constructs a simple interpretation. It feels like solid objects pressing against each other. But underneath that interpretation, there are no hard surfaces meeting. There are only fields interacting, forces balancing, quantum rules shaping behavior. The world feels solid, not because it is made of solid pieces, but because these interactions are incredibly stable and predictable, and that illusion is so convincing that we never question it. Until now. Now that we understand why objects feel solid, we can go one level deeper. Because atoms do not just resist each other, they also bind together. Everything around you, from the air to your body, to the structure of entire planets, exists because atoms can form stable connections. These connections are what we call chemical bonds. But once again, these bonds are not tiny hooks or mechanical links. They are patterns of interaction. When two atoms come close, their electron clouds begin to overlap in a controlled way. Under the right conditions, this overlap allows the system to reach a lower energy state. And in physics, systems naturally move toward lower energy whenever possible. So instead of pushing apart, as they would in simple repulsion, the atoms settle into a stable configuration. A balance. Take the simplest example. Two hydrogen atoms. Each hydrogen atom has one electron. When they approach each other, their electron clouds begin to merge into a shared region between the two. Nuclei. This shared region creates an attractive effect. The negatively charged electrons are now influenced by both positively charged nuclei, pulling the system together. The result is a bond. Not a physical connection, but a stable arrangement of electromagnetic interactions. The atoms are not touching. They are held in place by a balance of forces, attraction and repulsion. finding a precise distance where the system is most stable. This same principle applies to every molecule in existence. Water, oxygen, carbon dioxide, proteins, DNA, all of them are structures formed by electrons arranging themselves into patterns that minimize energy. Different elements create different patterns because their electrons occupy different configurations. Carbon, for example, can form multiple bonds in different directions, allowing it to build chains, rings, and complex three-dimensional structures. This is why carbon is the foundation of life. Every cell in your body, every molecule that carries your genetic information, every protein that performs a function, all of it exists because electrons can arrange themselves in these stable, flexible ways. And still, through all of this, nothing is touching. Every bond, every structure, every material is held together by electromagnetic interactions shaped by quantum rules. At this point, a deeper question naturally arises. If atoms are mostly empty space, if electrons are just probability clouds, if everything is held together by invisible forces, then why does matter not collapse? Why does your hand not pass straight through the table? Why does your body hold its shape at all? The answer lies once again in the Pauli exclusion principle. This principle does more than prevent electrons from sharing the same state. It creates structure at every level of matter. Inside an atom, it forces electrons into different energy levels, giving atoms their size. Inside materials, it prevents atoms from compressing indefinitely, creating resistance. Without this principle, all electrons could fall into the lowest possible energy state, collapsing matter into an extremely dense form. There would be no extended structures, no stable atoms as we know them, no chemistry, no life. Matter would behave in a completely different way, but because electrons are what physicists call fermions, particles that obey this exclusion rule, they resist being packed into the same configuration. This resistance creates what you can think of as a kind of quantum pressure. Not pressure in the everyday sense, but a fundamental resistance built into the fabric of reality. It is this resistance, combined with electromagnetic forces, that gives matter its stability. It is why solids remain solid, why objects hold their shape, why the world does not collapse into something unrecognizable. Even in extreme environments, this principle plays a crucial role. In stars, for example, when gravity tries to compress matter inward, quantum effects push back. In certain cases, this creates what is known as degeneracy pressure, a direct consequence of the exclusion principle. It is one of the reasons some stars can resist complete collapse. So when you look at the world around you, what you are really seeing is a balance between forces pulling inward and rules pushing outward, between attraction and resistance, between energy and structure. And this balance is maintained not by solid objects pressing against each other, but by the behavior of electrons, by invisible rules that operate everywhere, at all times, shaping reality in ways we never directly see. Up to this point, we have looked at the structure of matter and the forces that govern it. Now we turn inward. Because everything we have described so far, every electron, every force, every interaction, is not something you directly perceive. What you experience instead is a translation. Your senses do not detect reality, as it is at the quantum level. They interpret it. When you touch something, your skin does not feel atoms. It detects pressure. That pressure comes from electromagnetic forces pushing against the atoms in your skin. Specialized receptors convert that mechanical pressure into electrical signals. Those signals travel along your nerves, into your brain, and your brain constructs the feeling of touch. When you feel warmth, what is happening is not contact with heat as a substance. It is the transfer of energy. Atoms in a warm object vibrate more intensely. When your skin comes close, energy flows through electromagnetic interactions into your body. Your receptors detect this increase in energy, and your brain interprets it as warmth. When you feel cold, the process is reversed. Energy flows out of your skin into the object, and your brain interprets that as cold. The sensation is real, but what it represents is a pattern of energy exchange. The same is true for texture. A smooth surface produces consistent interactions across your skin. The forces are even, predictable. Your brain interprets this as smoothness. A rough surface produces rapidly changing interactions. Tiny variations in force across your skin create a complex signal. Your brain interprets this as roughness. Even sound follows this pattern. Vibrations in the air reach your ears, causing physical movement in tiny structures. These movements are converted into electrical signals, which your brain interprets as sound. Music, speech, noise, all of it is a translation. Light works the same way. Photons, excitations of the electromagnetic field, interact with the electrons in your eyes. This interaction triggers signals that your brain turns into color, brightness, and form. At every step, from the external world to your internal experience, the chain is the same. Field interactions, converted into signals, interpreted as reality. There is no direct access, only translation. And yet, the translation is so consistent, so reliable, that it creates a seamless experience of a solid, stable world. A world that feels immediate and real, even though underneath it is something far more abstract. Now we take one final step back. Everything we have described, electrons, atoms, forces, interactions, does not just apply to the world around you. It applies to you. Your body is made of atoms. Those atoms are made of nuclei and electron clouds. Those electrons are excitations of a field that exists everywhere in the universe. You are not separate from this system. You are part of it. The atoms in your body were not created recently. Many of them are ancient. The hydrogen atoms in you were formed shortly after the beginning of the universe. The carbon, oxygen, and nitrogen atoms were forged inside stars that existed long before the Earth. Those stars lived, burned, and eventually exploded, scattering their material into space. Over time, that material became part of new systems, planets, oceans, and eventually, life. The atoms that now form your body have been part of this long chain of events, moving through different structures, different forms, different systems. And now, for a brief moment, they are arranged as you, a temporary pattern, a highly organized system of interacting quantum fields. Your thoughts, your memories, your awareness, all of it arises from the activity of your brain. And your brain is built from the same ingredients we have been describing. Electrons moving, fields interacting, signals forming. You are, in a very real sense, the universe observing itself. A structure complex enough to reflect on its own nature, to ask questions, to understand. And what you have just understood is this: the world you experience is not built from solid pieces touching each other. It is built from interactions, from fields, from forces, from rules that govern how these fields behave. Nothing needs to touch for everything to connect. And yet, everything is connected. At the deepest level, there are no hard boundaries, only relationships, only interactions, only the continuous unfolding of the same underlying structure everywhere in the universe. And you are not outside of that structure. You are made of it. And now, as we slowly come to the end of this journey, take a moment. Let everything you've heard settle. Right now, wherever you are, whether you're lying down, sitting quietly, or just letting your thoughts drift, you are surrounded by a world that feels solid, stable, and familiar. The surface beneath you feels real. The air around you feels present. Your body feels grounded in space. And yet, at the deepest level we can understand, none of it is quite what it seems. The sensation of touch, the feeling of pressure, the experience of holding something in your hand, all of it is the result of invisible interactions. Fields meeting fields, electrons responding to electrons, forces balancing perfectly, moment by moment. Not contact, but connection. And somehow, from all of that, from these quiet, invisible interactions, emerges a world that feels warm, textured, and real. A world you can move through, a world you can experience, a world you can understand. You are not separate from this. You are part of it. A temporary, beautiful arrangement of the same quantum fabric that fills the entire universe. Every thought you've had during this journey, every image that formed in your mind, every sense of curiosity or calm, all of it is the universe, quietly observing itself. And if you enjoy these kinds of slow, deep explorations, you're always welcome here. On Science Sleep Theory, we take complex ideas like this and turn them into something you can relax into, something you can think about or drift off to. So if this helped you unwind or sparked your curiosity even a little, you can like the video or subscribe and join me again for the next journey. For now, let your thoughts slow down. Let the ideas fade gently into the background and rest, knowing that even in stillness, even in silence, the universe is still moving, still interacting, still unfolding, quietly, all around you. Good night.